Welcome to Tech and Test, where we unravel the intricacies of technology, delve into the world of software engineering, and challenge the boundaries of software testing. Your host, Peter Johnson, will help you navigate the digital landscape, exploring the latest in tech, sharing insights into software development, and talking to the people that drive our digital world. Now, let's dive into today's episode.
And welcome to another episode of Tech and Test. And with me here, actually in my living room, is Darendra, Appanah and James Banyard. Guys, welcome to Tech and Test.
Hello.
Hello, Peter. Great to be back.
Yeah, welcome. I think, Darren, you were here on episode 1, so welcome back. James, welcome to Tech and Test. Can you tell the Tech and Test audience a little bit about you?
Yeah, sure. So I work with Darren at the same company, but instead of a software test, I'm introducing hardware test to Tech and Test. I'm a hardware test engineer.
Right.
I do lots of stuff in electronics. I do some embedded system work. And I also do photonics, which I'm hoping to chat a bit more about.
Awesome. So what can we just start with, because in the room here, we've got a bunch of software test engineers who used to be software test engineers or STETs or whatever we call them, and also hardware. Like, can we define what hardware testing is to begin with?
Yeah, sure. So I kind of see hardware as everything that your guy's software runs on. I mean, it also includes stuff that doesn't have software, which I particularly like because there's less problems with it. But so anything electronics, your phone, consumer devices, test equipment. So that's the stuff I kind of work on and I validate to make sure that it works.
Okay, so what are we validating here? Are we validating the hardware design, the system design? Like, what kind of hardware testing techniques are we using to kind of test? What are we actually trying to test?
This is it, right? I think there's quite a lot of overlap between software and hardware, right? Because then you have unit tests in software where you're kind of testing the sort of smallest sections of your system. Then you also have system level tests where you've got everything kind of integrated and together. And that exists in hardware as well. So, you know, we will do our equivalent unit tests on the sort of individual circuits or as low level as it gets in our PCB or even just by itself. But then, yeah, we'll do integration tests where we bring those circuits together and see how they interact.
Right.
And then we'll do system tests. So see if the thing works functionally. And a lot of the stuff I do is more performance level testing. So it's how well does the design work? And so that's the kind of stuff that I enjoy the most. It's more like experiments, setting up stuff. But yeah, so that's it.
Awesome. How much of sorry, Darren's looking at me really interested in in the question we have at hand. But how much software do you have to write to test the hardware? Like, how much of your work is actually writing scripts or code to exercise the hardware?
So a lot of the stuff I actually do is to automate hardware testing.
Right.
Because you can imagine if you've got a PCB, a lot of things sort of you traditionally do is hook it up by hand.
Yeah.
Measure something with a specific device that measures it, and then you write down your values or you record your values. But if you're trying to do that 1,000 times, I'm not going to sit in the lab for 8 hours doing it. And so, yeah, this is it. For my software ability, it's a very practical use case. I want the thing to run something I would do manually 1,000 times, you know, generate a CSV file and then make a plot for me. So I'm very much on I'll get something to work with the software, but I'm not implementing proper software practices on my day-to-day. But it is invaluable to me. It's a tool, really.
Cool. Yeah, that makes a lot of sense. I think, to be honest, that's a lot of testing in general, right? Whether it's software testing or hardware testing, a lot of the coding and software engineering, in sort of quotes, is really to, as a tool to kind of exercise testing, get data and analyze the data, rather than it's a product in its own right. Darren, what are you currently working on? What are you currently doing or interested in?
So I'm working in the engineering assurance team at Cambridge Consultants now. So I've kind of separated from the system engineering and test department, which is what I was part of last time I was on the podcast. So that involves mainly AI assurance and cybersecurity as well. So we are working on projects where we have to ensure that the AI models that are being used on various systems and projects are safe, secure, robust, as well as meeting their performance and meeting the requirements and doing the thing they're supposed to do, really. So if you can imagine things like an autonomous vehicle, how do you make sure that it's, yes, going to do the things that you've specified that it will do, but also when it comes to edge cases or less common scenarios, let's say a child jumps in front of an autonomous vehicle. Yes, you can test whether it will avoid it, but will it avoid it in a way where it will then crash into a bus and cause catastrophic damage, or does it avoid it in a much safer manner, right? So that's some of the things I'm working on.
Awesome. Okay. So how much of your work actually is with the AI kind of models and looking at like labeling the data, checking what data was used for training models, basically like kind of the AI assurance space, and how much of it is more specific to maybe the project and technology that we're using? Like, how much do you think your role is changing by AI, basically? I guess that's the ultimate question, right?
Right. So when it comes to data and labeling, so typically we have our AI engineers who are doing that kind of thing. So they have their own ways of testing the data and sort of like unit tests for the models. I'm more on the sort of system level. What things are we doing? Or what things is the system doing itself, and specifying various test cases so that when we actually run the model, that it's behaving the same way that we want it to behave.
Awesome. Guys, can you say hello to Matilda, my cat? She's in the living room.
She's stolen a chair.
She's stolen the chair. She wants to be part of the podcast. So I thought I'd introduce her back into the podcast because on episode 1, she got mentioned. It's good to sort of catch up with her. Now, it's an interesting space, AI, and I think all of our roles in the next few years will be touched in some way by AI. James, what are your thoughts on AI? You're working with a lot of hardware at the moment. Have you seen changes in hardware design with AI impacting that? Has that been a factor in the work you've been doing?
This is it. I feel like people want to put AI in lots of different things. But actually, yeah, so some of the work I do in photonics in particular, there's mostly research papers, but there's in fact been a lot of sort of effort into how can you make AI designs for systems that are too complicated for people to sort of simulate and generate. So a lot of the photonics design we're working or trying to do at the company, you can simulate. You can create kind of like a model. There are software programs that do this, but they're super computationally expensive to do. So you could run a simulation for like days to try and verify that your model or your kind of the shape that you're trying to fabricate would be correct. Or you could use an AI model to effectively optimize your system. So in fact, it's really interesting to see the designs that they come up with. Humans like symmetry. We like shapes that kind of look very like, okay, I'm splitting something into 2 branches. It needs to look symmetrical. But the AI models, when they generate them, they don't have that bias. So theirs looks really wonky and kind of like spattered and spotty, but their designs will be more optimized. And it's because they don't have sort of those limitations that we put into design constraints. So there is value there. I think it's pretty early doors. I think a lot of the sort of AI solutions that even in the software space, right, they're not quite ready to replace our systems, but they are getting there, or they can be used in certain situations I think would be valuable. And so I'm always looking for it. I'm always like, what can it do for me? And there's some kind of like spaces that are really valuable it can sort of deliver in.
If you had to explain photonics to someone who
yes
who is onboarding with photonics, I'm trying to say this in the most like elegant way, but tell me what photonics is and what you're part of, or what you define as photonics.
I really hate the word photonics because it kind of feels like a buzzword to me. Really, all it is kind of in the name. So photon, it's a packet of light. I think it was named photonics. I think was named to kind of used photo and part of electronics. So in my head, and a lot of people's definitions, it is the practical sort of study of light. So photonics is a branch of optics, but it's the branch of optics where we're trying to do stuff to the light. So it uses a lot of semiconductor devices. So most of your imaging systems will be kind of related to this, and also fiber optics. So for me, most relevantly, it's telecommunication devices. And photonics has been around for a long time. I mean, like the 60s, since the laser diode really was founded. But it's now kind of, as the technology has kind of caught up, but also as we found a use for it, it's now branching out into more systems. And so we're finding use cases that sort of implement photonics that, you know, this is the technology of the future, and we're trying to develop more into this field.
What kind of interesting use cases and exciting new technologies are you finding in this space?
So one of the main ones I see from telecoms, which I think is most cool, is free space optical communication. So at the moment, a lot of the sort of telecom systems use fiber optics. So you basically have a bit of, glass effectively, and your laser light goes down this bit of glass. And if you want to go from, the UK to the US, you have to bury underground cable. And I know it's maybe a bit too relevant, but, some foreign entity could cut that cable, and that might be, problematic.
Yeah.
What free space optical comms is that same laser light, but through free space. So not through fiber.
Interesting.
And so what you get is all the benefits of high-speed data rates. So, fiber optics, technically can go up to hundreds of terabits per second, which is ridiculous. But free space optics can do, hundreds of gigabits per second over kilometers of distance. And, the 5G systems we have, they're like, okay, over a kilometer or so, maybe 5-6 gigabits per second. So it gives you a sense of photonic systems are orders of magnitude faster. And so the free space optical comms is like, okay, we can replace tons of sort of slow RF systems with none of the infrastructure. You can put them on moving targets. So one of the things, really interesting is putting them on autonomous vehicles, sharing information between moving targets at data rates, kind of insane speeds. This is the sort of stuff I love, because it's like, how far can we take sort of information technology by making it as cheap and accessible and high speed, and see what people can do with it?
Interesting. Yeah. So what are some of the, you've given me a whole list of positive use cases and potential use cases, and a vision that sounds awesome. Like the world's even more connected, right? Your autonomous vehicle is talking to your cell phone, and, vice versa. What are some of the negative or challenges we have with this technology that, is it bad, given power consumption is increasing, right? AI models are using a lot of carbon, right?
Oh, well, I'm gonna unfortunately say photonics is great for energy efficiency. Sorry, I'm just plugging more photonics before I give you a negative. But genuinely, I think for sort of parallel processing, in fact, this is it. One of the main things with AI is, there's all of these software companies trying to do AI, but they're recuperating a fraction of the cost because they're having to run on data centers on really inefficient machines.
Yeah.
So the computation per watt is really bad for electrical systems. But you can generate photonic circuits, so you can have photonic processors to do those sort of AI, large language model blocks for a fraction of the energy cost. Sorry, I will give you a negative at some point, but it's like there's so much photonics can do, and it's only just kind of being tapped in at the moment. And it is a new field. So it's a case of we really need to see how we can expand and how we can kind of improve our current systems from the hardware level itself. Because we can improve the algorithms.
Yeah.
The stuff it's based on is really what I think will give us the next leap.
Yeah, it's interesting. I think 10, 12 years ago, I think someone said to Congress that algorithms was going to be the next thing that gives us value. I think we've exhausted that in this current decade, right? Also, and now it's almost like the hardware needs to be customized everywhere we look. I think that's one reason Nvidia stock has been so valuable, right, recently. And the CEO of Nvidia will probably be the richest man in the world in a couple of years because of that. So interesting. What do you think of the barriers to photonics scaling out?
This is it. It is quite new, or at least the stuff we're trying to do now There isn't really the infrastructure there at the moment.
Okay. What is the infrastructure that you're talking about?
So there's a couple of things with that. There's what the chips are made of, and then how they're actually packaged and used. So one of the things that is a rising field, which is to kind of solve this infrastructure problem, is silicon photonics. So it's building these photonic chips out of existing infrastructure for sort of traditional electronic ICs. And so they can reuse a lot of the existing foundries and fabrication processes and sort of retune them to develop these new circuits. Depending on the material, you get different properties. So silicon photonics only fills sort of a small niche in the field. You still have to use other materials, so other semiconductor materials, to actually get certain solutions. The other aspect, though, is actually packaging the thing. So electronic packaging is really, really standardized and is really cheap. Photonic packaging isn't really. I mean, there's a lot that for sort of existing systems, but they're really sort of basic. Sort of classic IC is like a butterfly package, but it's got, between 12 and 24 pins, a very small amount. It is quite a large scale device. It could be the size of your thumb, basically. You need to build stuff that are the size of proper ICs, less than a centimeter wide, that sort of thing. So we don't have that system yet. And so places can build it, but not at scale. And so one of the things sort of I'm wanting to look into and make sure that the field is developing in that way is how to get photonics packaging sort of scalable and cheaper. Because once you can package it cheaper, the chips should be coming in as cheap as they come.
Yeah, so I'm kind of sensing that cost is one of the challenges with scaling photonics. And would you agree with that? Is that something that needs to come down for this to scale?
Yeah, exactly. But, the same happened with electronics. And it's once people see its value, they will invest the time and the technology and the research to bring down those costs, because then you can actually do it.
Awesome. Okay. So James, what do you think we can do today to help scale this technology and then improve society?
I think
it's a big question.
Not everyone can do this, but I think one of the things is thinking about application spaces that can use photonics. So what we have kind of is almost like a chicken and egg situation of we have this technology, but it's too costly, so no one wants to use it. And so no one wants to use it, so no one develops the technology.
Yeah.
But if we find sort of more niches and there are sort of more places starting to use it in more situations, then an industry builds up, and it happens really quickly once that ball gets rolling.
Yeah, I mean, we've seen this with, I don't want to keep quoting it, but with AI and large language models, AI is an old tech. There's a lot of old models and algorithms with, ML driven, right? AI is not new. It's been here for a long time. It's only recently we've seen this sort of scale in investment with new startups and new use cases that really has been driven by the investment that's come into AI recently, right? Off the back of OpenAI's large language model. Darren, you want to say something?
Yeah, so I would say one difference between what James is talking about with photonics and AI is that I think in recent times, lots of different companies and organizations have wanted to adopt AI without necessarily thinking about what the use case is or what the application might be, just because they want to have AI as part of their products or in their organization. So I think that's a really important message you just said there, James, is to really think about the application before investing in such technologies.
It is a bit of a buzzword as well, and like it gets into the culture. But I think the other aspect with AI is companies see it as quite cheap to implement. There's no sort of upfront cost. When in photonics, it's hardware, right? You have to dump millions of pounds at the start of the project. For AI, you just need to hire engineers effectively.
Yeah. You've got loads of models in AWS or Google that you can just switch on and just use and get value and integrate into your product. Whether that's like search recommendations for something or, speech to text or voice or, computer vision, whatever, it's all there for you to use. no millions of pounds or dollars investment required, right? So yeah, but I kind of agree very much so with what Darren has been saying, which is, photonics, you're focusing on the use cases first, right? And I think because there's like a high bar to cost with this, it's critical and paramount that that's actually being used. You think those things through up front rather than just integrating AI and just using it because it's the next buzzword. And I think that's really cool. And Darren, you're still here, right?
I am still here. Thank you for noticing, Peter. So I've got a question for you, James. What would you say to investors to convince them to invest such large sums of money into photonics? What kind of benefits and use cases would you be able to sort of illustrate to them?
Yeah, exactly. So, I mean, I touched on this a bit, which is the benefits of the technology. But the reality is, if you're going to invest money into this, I think one of the first things they kind of care about is like return on investment. One of the things we're seeing in AI, right, is there's an issue with cost for each process that's happening. So photonics 100% can solve that as a problem. We can reduce the sort of cost of implementing these AI systems, even just sort of normal computation systems, and reducing that cost makes more businesses more viable. Then there's also the flip side of that is if you're using less energy, it's more sustainable. So these data centers, right, they require enormous amounts of power. And we're still not on renewables yet. At least most countries aren't. So we're kind of like creating a system where we're putting more processing into non-renewable resources. We're using up more water. And so if we're making our hardware more efficient, we're making all of our sort of tech more sustainable in general.
Great. Thanks, James. So bringing it back into test now. So when you're working on photonics projects, what sort of things do you have to consider for testing?
Yeah, I mean, that's good because from my electronics background, I feel like I had some sort of presumptions on how to do photonics test, but it's really unique in the way that you have to do test. So one of the kind of things is it's really hard to probe a signal. So in electronics, pretty easy if you've got a PCB. You get your oscilloscope, you get your multimeter, you touch it to a piece of metal, and it's metal to metal, and you can read a signal. But in photonics, typically you're working in fiber optics, and so there's no real way to probe fiber in that sort of nice, easy, cool, I'm just going to sample here. You have to split off your signal. You have to physically connect, move things around, or what I've sort of discovered is your system has to have test built into it. So a lot of the systems I kind of want to build, they have optical switches. So at any point I know I want to measure, I have a sort of signal path that is nominal where, my device should be operating. If I want to probe it, I have to kind of have it split off or switch to a case, and I can then sample what that thing is. Because ultimately, this is light we're talking about, and it has to convert to electrical signal at some point. So I have to put it into a separate device to actually measure it. So a lot of the time when I'm building sort of test fixtures and test rigs for photonics, I really have to understand the thing I am testing at a really fine detail so that I can actually test it properly. When in electronics, typically, you just need to look at the schematic and know what points you need to probe. It's a lot more of a different beast.
Interesting. So what kind of testing are we actually doing with those sort of circuits then? Is it more why would you want to split the signal off and check the signal? Are we looking for amplitude? Are we looking for specific, what are the kind of key important things when we're sort of testing these systems that maybe differ from a sort of electronics-based system?
There's a lot of stuff that is similar, particularly in telecoms, because the reality is photonics in telecoms is the same as electronics for telecoms. It's just using light. So we care about things like signal to noise ratio. You care about, what is your bit error rate? How much data can you actually transfer? So those skills are actually transferable for photonics. So a lot of the electronic stuff I learned for that test was usable. And in fact, even, things like noise and the way that sort of error propagates is still valuable there. It's just that, actually measuring it is the difficult part.
Do you think that, like, we're talking at the hardware level here, right? But if we go a little bit further up from the hardware level, we're talking like networking, right? Are the sort of network or the protocols we built for networks which use standard electronics, do they need to change a little bit for this new photonics? If we're dealing with a lot, larger data sample and data throughput, are they sufficient? Or is there sort of research into looking about how we can, improve our current protocols for this technology? Or is that even relevant?
That's actually a great question. I think you've touched on something that in the field,
right,
a lot of the sort of photonics and telecom stuff reuse existing protocols.
Yeah.
And in fact, a lot of it actually is reused from the old analog television. So a lot of those systems are kind of used in photonics because we have so much more bandwidth that we can work with. But what you're suggesting, I think that this is actually the root of the matter of, because photonics isn't that widely used, there aren't as many sort of, optimized protocols in the same way, other than what's already been sort of brought from RF and electronic systems. So we could in the future see new ways that it's optimized because, there are different ways and properties that the light works that we could encode the information differently. So it's a bit of a balancing act. And there probably is research out there that people have sort of looked into different protocols at this level.
So with optical communication, so do you think it'll ever replace traditional RF comms?
Yes and no. I hate that as an answer, but that's true. It will replace certain systems. I think RF is super useful. Like, I don't think in certain scenarios you can ever replace it. For optical telecoms, it's a case of if you need enormous amounts of data throughput, that's when you start to get limited. There's basically only a certain amount of bandwidth you can handle. But, for systems where I think, in fact, one of the things RF is really good for is going through walls. A lot of optical systems can't do that. Unless your walls are already pretty transparent, you can't,
Yeah.
Unless you've got a glass house. But yeah, so what we'll see is things like 5G, 6G, those systems, I believe, might be replaced by free space optics. So you can see like where we're hitting the limit in the hardware there, we can then go, there's a solution there that we can fit sort of now photonics to replace, but it won't replace everything.
No, but also in particular use cases, I think maybe it won't be able to replace it either. For example, like if you got certain weather conditions or light conditions around you that interfere with your signals.
It's true. Yeah. I think one of the things, in fact, this is free space optics, right? One of the things that people are working on is how to build robust systems like that. And so you have the algorithms people who want to see if they can actually still get signals through clouds, through fog, thing like that. And the other guys who are saying, okay, how robust can we make the infrastructure around it? So instead of point to point, can you build a big enough network that your light can sort of navigate around the system, around the clouds? Or like say, can we just have RF to replace if there's downtime, certain systems? So the great thing is there isn't one solution, but photonics enables you to solve different problems.
Yeah, and I think it's really exciting to be using some of these new technologies now.
Yeah. So I feel like I do a lot of hardware stuff. I don't do a lot of software stuff. And a lot of the photonic stuff I work on is new. And it's kind of a field that, test isn't that developed in. I don't know what it's like for you guys working in, things like AI. I feel it's undeveloped. What's it like to test these systems?
So that's a really interesting question, actually, James, and I can bring it to cybersecurity and AI, actually. So I'm talking about trying to test for security vulnerabilities that have maybe just been discovered or not quite yet been discovered. The tools for testing them are very immature. There might be things like proof of concept scripts that somebody's made for a research paper, or just a paper talking about what one might do to discover some of these vulnerabilities. And it is quite challenging when you have to actually do this on a project. It takes quite a lot of effort to take some of these tools sometimes that you might find that someone's published on GitHub or somewhere that you can access openly on the internet. And because they are just trying to prove that you can exploit such vulnerabilities, it's not been created as an actual product. So what you then have to do is adapt that tool or develop it further to make good use of it. So that's one challenge. The other challenge is actually trying to understand what exactly you have to do, because I'm talking about academic research here compared to something that's standardized and everybody knows about, you learn about when you're doing your degree, right? And for me, that's kind of the main challenge, because, coming into this field and trying to learn about this brand new technology, and there are lots of gaps in knowledge because it is all very new. To me, that was another challenge.
So yeah, it feels like you're almost doing academic research, but you're having to then implement it. So even as a tester, you're almost doing engineering just to get the tests set up.
Yeah, exactly that. So it's actually taking that research even further. So what I can say is some of the papers might stop at a particular stage and say, hey, we found a way of exploiting this particular vulnerability. You then have your own particular use case for whatever project you're working on, and you have to then further develop that and understand and discover new ways of trying to exploit the same vulnerability. So yeah, it is a bit of R&D and doing academic research, and it can be quite time consuming.
Does sound fun though. I feel like getting to work on this kind of new stuff, even if it's difficult, that makes your day pretty fun.
It is fun. Some aspects can be fun, but some aspects can also be quite demoralizing. For me personally, it's when I spend quite a lot of time reading something, and it sometimes makes me feel even more stupid.
Yeah.
But
don't worry, I also get that.
Yeah. So that's the non-fun part of it. But yeah, actually, once you've understood what you need to do and you've worked at it, you've tried a few different things, and you've finally developed something that actually works in exploiting particular security vulnerabilities, that's actually really great.
Have you worked on these sorts of things as well, Peter?
So when we say these sort of things, right, we're talking about AI systems which are, released to production, essentially.
Or new tech.
New tech. So there's a whole bunch of new tech I've worked on. And for a whole bunch of NDAs, I probably can't talk about them specifically, but some of the challenges in general with new technology, right, is lack of tooling. So often you want to write loads of automated tests and have quick feedback. Usually those tools are not there, and they need to be developed. So that's the first kind of thing. Getting access to information. I think, James, we touched on this earlier when we were sort of walking in and discussing around, there isn't always a lot of documentation or papers, or you may be the first person in the room trying to do something, and you could be the industry leader at that point. So you could be the author of the first paper in that field. So I think that's a challenge. You've got the academic kind of isolation. You can't review loads of papers and contribute and review more and add that into your product. So that's something that is also key. And I think it is really that sort of like isolation, I think, that you have, where you can't go to your LinkedIn network or your ex-colleagues and really ask them for their experience, because they're not working on that particular technology, which is very niche. So here I'm talking about very deep tech systems, right? Most of the time I've been working on, general AI models that have already been released to production. And then it's more of a data training issue. What the model's been trained on, and you're really just testing from a user perspective. The results are reasonably acceptable. There's always going to be edge cases and error cases, but fundamentally that's more of a solved problem. But the non-deterministic fashion of some of these systems makes it hard to automate and test, because then we have to think about, what are we trying to test here if the system by definition is non-deterministic? And a good example of this is a speech recognition, automatic speech recognition system, right? You give it an audio file with some speech or some text, and you expect the translation of that in text. And you do a whole bunch of improvements to the model. Then is the model, say for example, there's punctuation that comes out of this, is that actually improvement, or is that like actually regressed in behavior? So understanding that non-deterministic behavior is a challenge. And the same thing could be for like personalized, maybe let's say you work for Amazon or something and you're personalizing some of the shopping experiences of what products are recommended for a particular account. Are those products correct? Those are the sort of challenges I think we have with testing AI systems, the non-deterministic thing and approach. And there is no easy answer, I think. I think a lot of it comes down to how the model is validated in the beginning. And when you're trying to test this from a system perspective, that's when it becomes more challenging with, what are we trying to test? And are we trying to test the back end is working with a database, right? Do we really care at this point what the model is giving in terms of recommendations? Because if we're just testing like integration testing, we can remove the AI bits out of this and go, we're just testing that integration. And I think that's it kind of makes our testing more focused and more explicit. And I think that's a good thing. I think AI has kind of shaken or should be shaking the testing pyramid a bit and going, which bits of these are we really testing, right? Are we validating the model? Or are we testing the API? Are we testing for performance? Are we testing for usability? And the list goes on. But
I feel like this is a common issue across test is how well can you define what you're testing? Because if you don't define it well enough, you could be testing forever. Because in fact, this is it, which kind of wrap full circle. One of the ways I kind of got into test was I did electrical engineering at uni, but I did a physics degree as a conjoint. And I actually found a lot of the tests I would set up would be like an experiment. And it would be quite sort of procedural and methodic and basically isolating the thing you're trying to test. And that actual skill was transferable for me. But it's that same thing of, okay, trying to isolate it, I have to build that test framework, that structure around it. And it doesn't matter if it's software or hardware, it's the same kind of problem. And they're transferable skills. This is it. Between software and hardware, although I cannot do it, I cannot do your guys' software, I feel like we can chat about it and it's we have lots of the same problems.
Great. And thank you. Thank you guys for coming to the Tech and Test podcast. Really appreciate it. Thank you for your time.
It's been great.
Been great. Darren, thank you.
Yeah, thank you, Peter. Happy to be here again.
Great. And I hope you've enjoyed not only coming on the podcast, but also the beer that we've been drinking. I think that's...
Yes. Well, we could have gotten away with that.
Great. Thank you, guys. Really appreciate it. Is there any final comments you want to say to the Tech and Test audience?
I mean, yeah, so I talked about photonics. Well, I talked about it from a surface level on this podcast, but if anyone's interested, I think you guys should connect with me on LinkedIn and... it'd be great to talk to you about it.
Cool. And if they want to find you on LinkedIn, James, what's the best way? Is it James?
It'll be James W. Banyard, I believe, or JW Banyard.
Cool. Awesome. Darren, any funny comments?
Yeah, I'd just like to reiterate that when people are thinking about adopting new technologies, really think about the application and what is going to be involved in adopting it and implementing it as part of your processes or businesses, rather than just jumping in to immature technologies.
Hello, it's Peter. Thank you for listening to this episode of Tech and Test. I personally appreciate it, and I hope you got something out of it too. If you're interested in subscribing, please do, because then you don't miss any episode I've created. And you can also visit techandtest.co.uk, which has all the episodes that I've created. And you can visit peterintest.com for my personal blog too. So I'll see you on the next episode.